Every computer you have ever touched has been fighting a war since the moment it was built, a war against its own electricity. Somewhere in Austin, Texas, a small team just switched sides. And if what they are building actually works the way they say it will, the machine sitting on your desk, the server farm humming behind your favorite app, even the supercomputer that takes up an entire warehouse, none of them will ever look the same again. To understand why this matters, you have to understand what a computer chip is actually doing every single second it is turned on. Inside that thin sliver of silicon are billions of transistors, tiny switches that flip between two states, on and off, 1 and 0. Every photo you have ever opened, every video you have streamed, every message you have sent, all of it is just an unthinkably fast sequence of these switches, flipping in perfect, disciplined unison. And that word, discipline, is the whole story. Because electricity does not want to behave. Electrons are chaotic by nature. They jiggle, they drift, they get knocked around by heat. And left alone, they would never produce anything as clean and precise as a 1 or a 0. So engineers had to force order onto chaos. They built circuits that fight constantly against natural randomness, correcting errors, filtering noise, and holding voltage levels rigidly in place so that a 1 always reads as a 1 and a 0 always reads as a 0. That fight is not free. It costs energy, and energy turns into heat. The faster you push a chip, the harder it has to fight and the more heat it throws off. This is the exact reason your laptop has a fan. It is the reason gaming desktops have towers of aluminum fins and spinning blades bolted directly onto the processor. It is the reason data centers, the massive buildings packed with racks of servers that run the entire internet, spend staggering amounts of money and water just keeping their machines from overheating. Some of the largest AI training facilities being built right now consume as much electricity as small cities, and a huge portion of that electricity is not even used for computing. It is used for cooling the computers that are computing. We built an entire civilization's worth of infrastructure just to stop chips from melting themselves from the inside out. It helps to remember that this was never really a hardware problem alone. It was a strategic bet the entire industry made decades ago, back when the pattern known as Moore's Law first took hold. The idea that the number of transistors we could pack onto a chip would roughly double every couple of years, making computers faster, cheaper, and smaller at a pace that felt almost magical. That pattern held remarkably well for decades, and it shaped everything about how we think computers should improve. Faster always meant smaller transistors, packed closer together, switching at higher speeds. But every one of those improvements also meant more heat concentrated into a smaller physical space. Cramming billions of switches closer together and firing them faster is, from a purely physical standpoint, very close to building a tiny furnace. And engineers have spent the better part of 2 generations finding increasingly clever ways to keep that furnace from destroying itself. For 70 years, the answer to this problem was always the same: fight harder. Shrink the transistors so they use less power. Improve the materials so heat moves away faster. Design smarter fans, liquid cooling loops, even chips submerged directly in special non-conductive fluid. Every generation of computing has been an arms race against heat, and every generation has won that race through brute force engineering, not through rethinking the fundamental approach. The transistor stayed the same. The 0 and 1 stayed the same. The war against randomness stayed the same. We just got better at winning that particular war, generation after generation, until very recently, when the returns on that strategy started to shrink. Now here is where the story gets strange, and where this small Austin startup called Extropic enters the picture. Their founder, a physicist named Guillaume Verdun, spent years working at the intersection of physics and machine learning before starting the company, studying the kind of quantum and statistical systems most engineers only encounter in graduate textbooks. That background matters because it shaped the question he eventually asked, one that sounds almost too simple to be revolutionary, and yet cuts directly against 70 years of accumulated engineering wisdom. What if we stopped fighting the randomness? What if, instead of spending enormous energy suppressing the natural chaos of electrons, we built a chip that used that chaos as its raw material? It sounds like a paradox because we have been taught for decades that noise is the enemy of computing. Noise causes errors. Noise causes crashes. Every engineering decision in modern chip design assumes that randomness must be eliminated, filtered, or overpowered. But there is an entire branch of physics, one that deals with probability, uncertainty, and the statistical behavior of huge collections of particles, where randomness is not a bug, it is the entire mechanism. Thermodynamics itself, the science of heat, energy, and disorder, is built on the idea that systems naturally settle into probable states. Verdun's idea was to build a chip that computes the way physical systems already behave in nature, letting electrons wander and settle according to probability instead of forcing them into rigid binary positions. The result is a new kind of processor Extropic calls a thermodynamic sampling unit, or TSU for short. Instead of transistors that represent a strict 0 or a strict 1, a TSU is built around something called a probabilistic bit, or p-bit. A p-bit does not sit still in one state. It flickers between possibilities, weighted by probability, the same way a coin spinning in the air is neither fully heads nor fully tails until it lands. Traditional chips spend a tremendous amount of energy forcing electrons to behave like that coin has already landed, freezing every switch into a clean, stable position. A TSU does something almost the opposite. It lets the coin keep spinning, and it reads meaning directly out of that spin. This matters enormously for a certain category of computing problem, and it is worth being honest about which category that is, because this is not a chip that is trying to replace the processor inside your phone or the graphics card rendering your favorite game. Many of the most important frontiers in modern computing, especially in artificial intelligence, are not really about strict deterministic math. They are about sampling. When a large language model generates the next word in a sentence, it is not calculating one guaranteed correct answer. It is sampling from a cloud of probabilities and picking a likely outcome. When an image generation model creates a picture from noise, it is running a process that gradually shapes randomness into something coherent step by step, guided by probability at every stage. When scientists simulate molecules, weather systems, or financial markets, they are constantly running processes soaked in uncertainty, trying to explore huge spaces of possible outcomes and find the ones that matter. It is worth sitting with that idea for a moment because it reframes almost everything we think we know about what artificial intelligence actually does at the hardware level. When people picture an AI system thinking, they often imagine something like a giant calculator crunching exact numbers to arrive at one correct guaranteed answer. That mental picture is mostly wrong. Modern generative AI is closer to a weather forecaster than a calculator. It does not know exactly what will happen next. It builds a probability cloud over many possible outcomes, and then draws a single likely result out of that cloud over and over again, billions of times, to produce coherent language, images, or decisions. Every one of those draws is, at its mathematical core, an act of sampling from uncertainty, which is precisely the kind of task nature performs constantly and effortlessly, and precisely the kind of task traditional binary hardware has to simulate through enormous amounts of extra computation. Classical chips are remarkably bad at this kind of work in one very specific way. They are perfect calculators, but perfect calculators have to fake randomness. A traditional computer cannot actually generate true random behavior on its own. It has to run complicated mathematical formulas that produce numbers which only look random, a process that takes real computational steps, real clock cycles, and real energy, purely to imitate something a chaotic electron does naturally and instantly for free. Extropic's bet is that if you build hardware where randomness is not an illusion you have to manufacture, but a physical property that is simply already there, you can skip an enormous amount of wasted computation. You're not fighting physics to fake randomness. You are borrowing randomness directly from physics. And this is where the cooling question becomes so important. Traditional chips generate heat largely because of that constant fight to suppress natural noise and force deterministic outcomes at incredibly high speeds. A thermodynamic chip, at least in its room temperature form, does not need to wage that same war. It is not trying to overpower the natural jostling of electrons. It is choosing to work with it. Extropic's semiconductor-based TSUs, the version built using ordinary transistor technology rather than exotic superconducting materials, are designed to operate at normal room temperature, using standard fabrication processes that any modern chip factory could theoretically produce. No dilution refrigerators, no liquid helium, no warehouse-sized cooling systems keeping the processor near absolute zero. It is meant to slot into a regular server rack or even a desktop expansion port, the same way a graphics card would, drawing power the same way, but consuming, according to the company, dramatically less of it for the specific tasks it is built to handle. It is worth pausing here to separate the marketing from the physics, because this story has genuine substance underneath the excitement. Extropic actually has two parallel hardware efforts happening at once. The first is that room temperature semiconductor version, built for practicality, meant to be manufactured at scale using existing chip foundries, and meant to slide into today's computing infrastructure without requiring anyone to build an entirely new kind of data center. The second is a more exotic superconducting version, built using something called Josephson junctions, tiny circuits that only behave the way Extropic needs them to when cooled down to temperatures near absolute zero. That version absolutely does need serious cooling, arguably even more intense cooling than a traditional chip, because it is trying to reach the most extreme edge of energy efficiency physics allows. Verdon and his team have described these superconducting circuits as some of the most energy-efficient computing elements that could ever exist, since they operate almost entirely passively, drawing power only during the brief moment they are actually being measured. So when people say this chip does not need cooling, they specifically mean the room temperature semiconductor version, the one built for mainstream deployment. And that distinction matters because it shows this is not a single miracle device. It is a strategy with two tracks, one aimed at immediate, practical, plug-and-play adoption, and one aimed at a much longer term, much more extreme efficiency frontier for customers who already have the infrastructure and the budget for cryogenic cooling, likely large research institutions, government labs, or major cloud providers, chasing the absolute limits of energy-efficient computing. The efficiency numbers being discussed are dramatic, and it is important to hold them with the right amount of caution, because this technology is still extremely early. Verdon has described gains in the range of 100 times better efficiency for certain workloads and in specific favorable cases, numbers as high as 10,000 times better. Those figures come from tasks that align perfectly with what a thermodynamic chip is built to do, meaning heavily probabilistic sampling tasks, not general-purpose computing. If you tried to run a spreadsheet, edit a video, or browse a website on a TSU, it would either struggle badly or simply not be built for the job at all. The value here is narrow but potentially enormous, aimed squarely at the sampling-heavy backbone of modern generative artificial intelligence, robotics that need to make fast, probabilistic decisions in unpredictable environments, and scientific simulations that already run on techniques called Monte Carlo methods, a family of algorithms built entirely around repeated random sampling to approximate complicated answers. This is also exactly why the story connects so directly to the energy crisis, quietly building underneath the entire artificial intelligence industry. Training and running the largest AI models today requires staggering amounts of electricity. Companies building next-generation data centers are now negotiating directly with power utilities, sometimes even proposing to build or restart nuclear power plants, just to guarantee enough electricity for a single AI campus. Cooling those facilities consumes an enormous share of that electricity on its own, because every unit of computation produces heat that has to be pulled out of the building constantly, day and night, using massive chillers, water systems, and increasingly liquid cooling loops that run directly over the chips themselves. If a meaningful portion of AI's most power-hungry workloads, specifically the sampling and generative portions, could be shifted onto hardware that consumes a tiny fraction of the energy, the impact would ripple through the entire industry. It would not just save money. It could determine which companies and even which countries can afford to keep building bigger and more capable AI systems without hitting a hard physical ceiling on available electricity. But before this starts sounding like a done deal, it is worth being very clear about where the technology actually stands right now, because the honest answer is that it is still in its early, fragile proof-of-concept stage. Extropic's first real chip, an experimental piece of hardware the company refers to internally by an early code name, exists mainly to prove that probabilistic bits and thermodynamic sampling actually work reliably inside ordinary silicon, at room temperature, using processes a normal chip factory could reproduce. That first chip is not capable of running today's massive language models or generating sophisticated images. It is a foundation, a proof that the physics behaves the way the theory predicts, not yet a finished product ready to replace a graphics card in a real AI data center. The company has already described a planned successor chip, a far larger design intended to include hundreds of thousands of probabilistic bits working together, which would move much closer to something genuinely useful at scale. But that chip is still in development, still being designed and tested, and has not yet been proven in the real world, the way today's GPUs have been proven across years of continuous, demanding, everyday use. There's also a much deeper challenge hiding underneath the hardware story, one that rarely gets enough attention in the excitement around a flashy new chip. You cannot simply take an existing artificial intelligence model, one built and trained for a traditional processor, and drop it directly onto a thermodynamic chip, expecting it to work. The entire mathematical structure underneath today's most popular AI models, the transformer architectures behind large language models, and the diffusion architectures behind image generation tools, was designed with traditional binary computation in mind. A thermodynamic chip does not think in the same language. It requires new kinds of models built specifically around probabilistic sampling from the ground up, models Extropic calls, denoising thermodynamic models, an entirely fresh category of algorithm designed to take full advantage of hardware that natively thinks in probabilities rather than fixed numbers. That means an entire new layer of research has to be built alongside the hardware itself, new training techniques, new software tools, and an entirely new generation of engineers who understand how to design intelligence for chips that behave more like physical systems than calculators. History does offer an encouraging parallel here. Graphics cards were originally built purely to render video game graphics, and it took years of dedicated research before anyone figured out how to repurpose that same hardware to train deep learning models, eventually sparking the entire modern AI boom. It is entirely possible that thermodynamic computing needs a similar multi-year runway of dedicated research before its true potential becomes obvious, rather than something that transforms the industry overnight. It is also worth placing this alongside the other headline-grabbing approach to next-generation computing, quantum computing, because people often confuse the two, and the differences matter enormously. Quantum computers rely on qubits, which can exist in a delicate blend of states simultaneously through a phenomenon called superposition, and that fragile blend collapses the instant it is disturbed by heat, vibration, or stray electromagnetic noise from the outside world. That is precisely why most quantum computers today live inside massive dilution refrigerators, chilled to temperatures colder than deep space, just to keep their qubits stable long enough to perform a calculation. A thermodynamic chip is not trying to preserve some delicate quantum state at all. Its probabilistic bits are behaving classically, not quantum mechanically, simply embracing the ordinary thermal noise already present in any warm object, which is exactly why the room temperature version does not need the same extreme isolation a quantum processor demands. In other words, this is not quantum computing wearing a different name. It is a completely separate idea, sitting somewhere between traditional digital chips and quantum processors, borrowing the humility of quantum computing's respect for physical randomness while keeping the practicality of ordinary silicon manufacturing. Independent experts studying this field tend to agree that the idea is scientifically sound, while also urging real patience. Researchers working on thermodynamic and physics-based computing at major universities have pointed out that turning a promising physical principle into a complete, reliable, manufacturable system that performs consistently in real-world conditions remains one of the hardest unsolved problems in the entire field. It is one thing to demonstrate a beautiful effect in a small prototype inside a controlled lab environment. It is an entirely different challenge to manufacture millions of identical chips at scale, integrate them into existing computer systems, write software that programmers can actually use without a physics degree, and prove the technology remains reliable across years of continuous operation in messy, unpredictable real-world data centers. Extropic is betting that its room temperature approach, built using standard silicon manufacturing, rather than some exotic new material nobody knows how to mass produce, gives it a genuine shortcut through that valley of engineering difficulty. Whether that bet pays off is still an open question, and probably will remain one for at least the next several years. There is a practical business logic underneath all of this too, one that goes beyond pure scientific curiosity. Chip companies live and die by manufacturing pragmatism. Building a device out of some exotic new material that no factory on Earth knows how to produce at scale is a wonderful way to stay a laboratory curiosity forever. Extropic's decision to build its room temperature version using standard transistor technology, the same silicon processes that already churn out billions of ordinary chips every year, is a deliberate strategic choice, not an afterthought. It means that if the underlying physics keeps working as the company scales up its designs, the path to actual mass production does not require inventing a brand new industrial supply chain from scratch. It could, in theory, ride on the back of manufacturing infrastructure that already exists, which is a very different and far less risky proposition than something like room temperature superconductivity, a holy grail of physics that remains stubbornly out of reach. Still, it is hard to overstate how significant it would be if even a modest fraction of these efficiency claims hold up once the technology matures. Imagine data centers that need dramatically less cooling infrastructure for their most demanding AI workloads, freeing up massive amounts of electricity and water that currently exist purely to fight heat rather than produce anything useful. Imagine robots operating in unpredictable, chaotic real-world environments, using onboard chips that naturally think in probabilities rather than forcing every decision through rigid, power-hungry binary logic. Imagine scientific researchers running enormous molecular simulations or financial risk models on hardware that mirrors the very probabilistic nature of the systems they are trying to understand in the first place, rather than translating everything into a clumsy binary approximation first. None of this requires exotic quantum computers operating near absolute zero and shielded from every stray vibration in the building. It only requires a fundamentally different way of thinking about what a computer chip is even supposed to be doing at the physical level. That is really the deepest idea buried inside this entire story, more important than any single efficiency number or prototype chip. For the entire history of computing, we assumed that intelligence and precision required fighting against the natural chaotic behavior of the physical world. We assumed order had to be imposed from the outside, a tremendous energy cost, because nature itself was considered too messy to trust directly with meaningful computation. Thermodynamic computing challenges that core assumption at its root. It suggests that some of the most difficult, most energy-hungry problems in modern computing especially the probabilistic backbone underneath today's artificial intelligence boom, might be solved more efficiently by cooperating with nature's randomness rather than spending endless energy suppressing it. It is also worth noting that Extropic is not operating in a vacuum. Once a scientifically credible idea like this starts circulating, it tends to attract attention from far larger players who have both the capital and the manufacturing muscle to move quickly if the underlying physics proves out. Chip giants and cloud computing companies are already spending enormous sums chasing efficiency gains anywhere they can find them, from custom chips designed for specific AI workloads to neuromorphic processors inspired by the structure of the human brain. Thermodynamic computing is best understood as one more entry in that broader race, distinct from neuromorphic designs and distinct from custom digital accelerators, but part of the same underlying pressure pushing the entire industry to look beyond simply shrinking transistors and adding more of them. Whether Extropic specifically becomes the company that proves this idea at massive commercial scale is still genuinely uncertain. Hardware companies face brutal odds, immense capital requirements, and fierce competition from massive, well-funded incumbents who are also racing to solve the exact same energy crisis using their own very different approaches. But the underlying scientific principle driving this effort, the idea that physical randomness can become a computational resource rather than an obstacle to be eliminated, appears to be gaining real traction across multiple research groups and universities, not just inside one ambitious Austin startup. That broader momentum suggests this is not simply a clever marketing story wrapped around a single prototype chip. It looks like the early stage of a genuinely new branch of computing, one that could eventually sit alongside classical digital computers and quantum computers as a third distinct approach, each suited to a different category of problem, each with its own strengths and each shaped by a fundamentally different relationship with the messy, unpredictable physics of the real world. So the next time you hear your laptop fans spin up or notice the low hum of a cooling system somewhere in the background of a data center you have never even seen, remember that noise represents decades of engineers fighting a war against randomness just to force a clean, obedient answer out of chaotic electricity. And somewhere in Austin, a small team is quietly testing the idea that maybe, for an entire important category of problems, that particular war never needed to be fought at all. Instead of forcing electrons into rigid discipline, they are letting them wander freely, reading meaning directly out of that wandering, and betting that the future of computing might not come from fighting nature harder, but from finally learning how to listen to what nature was already trying to compute all along. It is a strange, almost humbling thought that the answer to one of technology's most stubborn problems might not have required a smarter invention at all, just a willingness to stop resisting something that was sitting there in front of us the entire time, quietly doing the work, waiting for someone to finally pay attention. Maybe that is the real lesson hiding inside this whole story, that progress does not always look like force, and sometimes it looks like listening closely enough to let the noise finally speak.